is about race condition. Actually, it's not race condition, it's about something to do with synchronization problem. Okay? It's not just race condition. Okay, in this chapter, we're going to look into quite a number of things. First thing is mutual exclusion, and what are critical regions, and how to solve it using logs, semaphore, mutex, and some other algorithms. Okay. So whenever you have synchronization, we always have problems with issues with synchronization that can cause the result to not produce the accurate result. Okay, and this involves two or more processors. If you have one processor, then you don't have multi-processing, and therefore you do not have this problem. It only occurs when you have two or more and you start to share. Okay? The keyword here is sharing. When you share, you need to synchronize. Right? So each CPU has its own process to run. You can have multiple processes running on a single CPU, or you can have two CPU running, each one of them run one process. And that is also counted as multiprocessing. Okay? And of course, you have processor manager to coordinate and to synchronize, to help synchronize. Normally, your processor manager will be your operating system. Okay, synchronization is a critical component of your cloud computing, and in order to make it successful, you need to avoid problems that synchronization system can give you. Okay, this is one application example. You have the code that is written here. You have these simple instructions that is to perform that. So here 3bc plus 4 is actually here. And here you can imagine it's a simple machine language. Of course, it's not written in assembly language, but it's simple enough to be assume that this is a assembly language. Okay, so 3 multiplied by b, which is this. And then we got d plus d, and then we got f plus, so f minus g. And then here you multiply t1, which is this one, is c. Okay, and then t5 is basically this, not multiplied, this is power of f minus g. Okay. And then finally A equals T4 plus 4, which is this. T4 is basically this, 3 times B times C. Okay, T5 is the one that we're talking about. So we can actually assign each CPU to CPU.code is kind of silly example, but if you assign to different CPU, you need only one clock cycle, almost one clock cycle. Okay, for example, this T1, T2, T3, T4, T5, they can be executed using 5 processors, right? And they are independent of one another, so there is no synchronization needed, okay? Because they are not dependent on one another. For example, 3B, assuming that you have data already in B, so T1 can compute at any time, because it will not clash with T2. Because T2 is D plus E, right? It has nothing to do with 3 times B. So these two can run at the same time. The same thing, T3, F minus G, has nothing to do with the rest. They also can run at the same time. So these 3 instructions can be run by these 3 CPU at the same time. How about T4 and T5? Now this one has some dependency, because T4 depends on T1, right? And T5 depends on T2 and T3. That means T4 and T5 will only execute after T1, T2, T3 has been executed. Okay, so that means T4 will wait for T1 to compute. That means CPU, this CPU here, has to wait for T1 to complete before it completes. Right? The same thing for T5. T5 needs to wait for T2 to be completed, T3 to be completed before it starts. So this is the part where you have dependency. Okay? The first part there is no dependency, but the second part actually has dependency. So this dependency will require you to wait, and therefore you have to share the information, and then you have problems, right? If let's say T4 execute first, before T1 completed, that means T1 is not containing any valid data, and you compute T4, and your data will be, your result will be wrong. Okay? The same thing, T5, he has to wait for T2 to complete first. You cannot execute first. So there is some kind of order or synchronization that needs to be done here in order to allow this T5 to have valid value. Okay, finally, A, also the same thing, this is the final one. You take T4 plus 4 divided by T5. That means A needs, this computation for A needs to wait for T4 and T5 to complete. And it itself also needs to wait for T1, T2, T3 to complete. So this is the last part, dependency of all this. Okay? And you can assign this to another CPU, but of course that CPU has to wait. Okay? So the first, no dependency. You can run at any time, you can run in any order. This one, it has dependency. These two can run at different order, but T4 and T5 needs to wait for their respective data to complete it. Okay? A have to wait for T4 and T5. Okay? Okay, the same thing for this kind of problem. There's some, I think I haven't, this is, whether down later, because I want you to know what to change. Because there's some animation. And I also want to show you what to change. Because I haven't updated. Okay, here concurrency control. Actually, I shouldn't call it concurrency. I should call it. You can also call concurrency as well, but to make things more. Here actually should be parallel processing, because it's actually not concurrent processing. You see the CPU there, you've got multiple CPUs, so this one should actually be parallel. Okay? Because concurrent computing means you use same CPU, but you have multiple processors using the same CPU. Okay? When we say parallel computing, that means you use different CPU. Right? Here I'll just leave it as concurrency control because it also applies to parallel computing as well. But the actual one here should be parallel processing. This one also the same thing, parallel processing. I think that is a better word to use here. Right? Okay, in our exercise that we have done, normally we only look at the for loop because the for loop is the one that has a lot of require a lot of processing time to do. Then let's say, for example, the multiplication of your matrix, you require 2.5 seconds, even though your processor is running in gigahertz. Right? So that is the best place to put. So normally there's a for loop here. So do is basically as a for loop. So you can see from here, if you expand it out, because this is 123, okay, basically the loop will do this. The first loop will do this, the second loop will do this, the third loop will do this, right? Because I depends on the counter here. So initially it's 1, then you increment by 1, comes 2, and then by 1 comes 3, right? So in this case here, you can apply parallel computing. Why? because they are independent of one another. If B1 plus C1 has nothing to do with B2 and C2, right? So this one can execute in one processor, this one can be executed in one CPU, another one, here another CPU. So this three can be run in parallel. And that's what we did, right? We have multiple processors and the loop we try to assign to different threads, and each thread is computing the equation and then find the solution. And this is only applicable to or possible if they are independent of one another. Most of our problems are independent. That's why we can apply this problem. This is a non-typical example. Okay, I will skip this. Let me use the Okay, the common element in all synchronization, whenever you share, okay, you need to protect it, okay? So the code that is going to access shared data, okay, this is the code, and of course this code here is going to share the data, right? Or the code itself, you want to protect. Let's say you want only one processor to run this code. While it is running this code, other processors should not run this code, right? One at a time. The same thing for the shared data. You want only one thread or one processor to run alone, okay, without any other thread that's coming in and access the shared data, right? So this code here we call critical region. Okay, the critical region is actually a piece of code. Either you want to protect this code, you want only one process to run at a single time. You've got multiple threads that's coming in and they can run in parallel, right? But you don't want that, you want only one at a time. That means you got n, you allow one to enter. Once this one finished, you allow the second to enter. So here is just like a funnel. So you got multiple threads here. So this critical region, you only allow one. But here you can run multiple. So this is a critical region. Right? Either you want to protect this code or you want to protect the shared data or resources. Okay. Okay, this one is applicable to single processor or multi-processor. Single processor, that means you run concurrent processors on a single core, you will still have the same problem. So you want the critical region placed there. Okay? Or you have multiple processors, two processors for example, each one run one process, but yet you have two processes. Same thing, you run only one process there. And you use this, you identify where the critical region, and then you have to apply certain synchronization control in order to allow only one to access. Because you know if one access, only one access, you will not have race condition. Okay, there is a reason why we have to identify where the critical region and then we have to apply. How we apply and what we do, I'll explain in a short while. Okay, here it uses one example, producer consumer. I don't want to get into here first because this one is quite complicated to explain. We need a number of things. First thing is we need mutual exclusion, which I will discuss this. And then we have we also have something else that I remember here. You mentioned about buffer size and all that. So I'm going to skip this one first. I know there's a lot of animation here. I will come back to this later. Okay, but I want to explain something else more fundamental than this first. Okay, I want to start from here first. Actually, I don't want to use this slide because this slide actually is very difficult to explain. I want to start with this semaphore. But before this semaphore, let's talk about the problem first. Remember the critical region that I was talking about? It has something to do with this. Let's say I have this instruction here. A plus 1. I think I mentioned this in the practical, but let's repeat this again. So this A, I want plus 1. And I'm going to run this using multiple threads here. And this thread is going to run this code at the same time, right? Initially, let's say A is equals to 0. Okay? So what we want is, if let's say we run using a single thread, let's say in a for loop, right? So basically, you're going to have okay, here basically there's no for loop there because we have n threads running. But suppose we are going to do the same thing using a single thread, we're going to have for loop, right? Here I from 1 to 3, and then here is A equals A plus 1, right? So eventually, when we get to this point here, your A is going to be 3, finally. Yeah? But if let's say you run using multiple threads, and let's say here is 1 to 3, that means you need three threads. Here you don't have for loop, right? Because you got 3 threads, right? Equivalent to 3, 1 to 3. Here you have to use for loop because it's only a single for. Okay? So here there's no problem. Because this A is not shared with anybody, a single thread is using. But here you run 3 threads and this is shared. And they can run at any time. Let's see how we run it and see whether we can get 3 or not. So here is the time. Now this actually needs to be converted into machine language, because if you look at here, it's only single statement. So we assume that this is atomic, right? When we do addition, one process do the addition, it will be 1. The second process that will do this addition will be 2. Okay? Because initially it was 0. The first thread change it to 1. The second thread change it to 2. The third thread change it to 3. Finally, you get the same answer. But that is not the case, because this actually needs to be converted into machine language, right? So you got something like this. Let's say you use AX, and this is your A, and then you add X by 1, or you increment X, AX, and then you move A, AX. So this single statement is actually this 3 assembly language, okay? Now this tree is going to be executed by 3 different threads. So 3 different threads is going to run this at the same time. Suppose the nice case will be like this. Thread 0, thread 1, and thread 2. Okay? First one is doing this, so AX is going to be 0. Okay? So AX is going to be 1. And then A is going to be 1. Okay? Then thread 2 comes in, let's say it comes later. Then you read A into AX. A is 1, so it's 1. So AX is going to be 2 after you add, and then A is going to be 2. So it looks just nice. Okay, this one is going to be 2, AX is going to be 3, A is going to be 3. So everything looks nice. Okay, because they run like this. Okay? But this is not always the case, because when we run in parallel, this might run faster, right? Okay? So here eventually we get 3. But it can happen like this. Suppose you're running like this, and then here you also read. But you haven't updated that, so you are reading what? You're reading a still value of 0. Here you add 1, here also you add 1. This. So you add 1 as well, so you get 1 as well. And here you assign AX to A. So AX is 1, so A will be 1. But here you use the stale value because it has not updated when you read the AX, right? So you read 0, this guy also reads 0. And here when you update 1 as well. So by right it should be 2 here, but here you get 1, and here also 1. The worst thing is, this guy also do almost at the same time. It's also 0. AX is going to be 1. A is going to be 1. So write 1 into that, this one write 1 into that, this one write 1 into the same variable. Eventually A is 1. You see the result is wrong? Right? The same thing. If this thing is down below here, let's say, this one managed to write into 1, and this one is down below, and this one get A is equal to 1, so it update it to 2, for example. Okay? Let's say another scenario. Write it down here. AX is 1, AX is 1, so 2, because you update it. Okay, A is 2. Okay, but here, this guy is 1 also. AX update to 2. A is 2. So here is wrong. Here is correct, but here is wrong because this thread is fast enough to actually get this same value. Right? So you can see the first example, A was 1. The second example, second scenario, you got A equals to 2. And the first scenario, A is equals to 3. So you can see that the result is unpredictable, or we call it undeterministic. This is the meaning of undeterministic, meaning that you get different results every time you run. One time you run, you get good result. Second time you run, you get this result. Third time you get this result. This is Rick's condition. Okay? Now, if you look at the first example, why there's no risk condition, you get good result, first example, right? Because this one run first, this one run second, this one run third, right? If you look at all of them, right? How does it look like? It looks like this, isn't it? This result is correct. If you notice, you want this track to finish, this completely finish before the next track runs. And this one needs to finish first before the next track runs. That means this code needs to be run by only one track to completion before the next track comes. Then there will be no race condition, right? And that is the reason why we have to make this critical region. And for critical region, we want only one code to access. This is the reason. You know why we want one code to access? We got multiple, sorry, not one code, one track. Here we got multiple tracks, but we want only one track to access. The reason is because of this. See? If we allow one track to access at a time, then you get correct result. If they start to occur at the same time, then you always get different results. And this is race condition. Okay? So this critical region is, it means that we want only one track to access. But how do we make that? This is the topic of semaphore real types. Okay, I'm going to talk about semaphore first because mutex is the same as semaphore, except that it has some other features inside that. Okay, what is semaphore? Semaphore actually comes from a Greek word. The meaning here is sema means flag. Okay, flag in Greek. For means signal. Okay, you use the flag as a signal. Why is it called this way? Because this semaphore was coined by Dijkstra. Dijkstra is a computer scientist, and he lived, I think, near a train station. If I'm not mistaken. Maybe I'm just making an assumption. In the past, we don't have a computer system like what we have now. All the train is computerized. When it comes, it knows when it comes because it's computerized, right? But in the past, there's human that do the coordination. They have to coordinate because they got only one track, but multiple trains. Okay, you got multiple trains, and you have to go to this track. So, and this track is going to be very long, right? So you got one guy here, one guy there, and they have to signal with one another. They can't shout because it's so long. So what they do? They use the flag. Okay, the flag has color, and the flag, they tell the other guy what is going on here, what it's trying to do. So flag, you use it for signaling. Okay? That is semaphore. Basically, it's the same problem. Okay, you only have one track, and one train can enter at a time. Like you got multiple trains, right? And you use this flag to signal. Okay, and because of that, maybe the computer scientists figure out, okay, I call it semaphore because of this reason. He's a Dutch, but the word here actually is a Greek word. Sema means flag, for means signal. Okay, so that's history. And then the other one is mutex. This one is much easier to understand. It means mutual exclusion. Sorry. Mutual, mutual. Mutuality, and then ex here is exclusion. Okay, so what does it mean? Mutual exclusion means you mutually agree with all the tracks. If I enter, the rest must avoid entering. That's why it's excluded. Okay, once one track enter, the rest cannot enter. That is mutual exclusion. Okay, so it's some kind of agreement among them. So it's some kind of signaling also. You have to tell the other track, okay, if I enter, you don't enter. Only me enter. Once I finish, I'll signal to you, and then the rest of the tracks will have to fight to enter. Okay, so the one that is winning will enter. The rest have to wait. So that is mutual exclusion. It's the same thing. Okay, it's the same thing, just different. Okay, I'm going to talk semaphore because semaphore was the one that was introduced first. Mutex comes later, and why we need that I'll explain in a short. Okay, semaphore is very simple. Actually, when he came up with this idea, he said, okay, basically what we need is a counter. Okay? Now this counter is going to count. If let's say I have, the counter is 3, that means I allow 3 to enter at the same time. Okay? And now it's very funny because I mentioned to you just now that mutex, we only want 1, right? But he wants to make it generic, meaning that he wants to control as many tracks that he wants. Because if I set my counter to 1, that means 1 only. But if I set my counter to 3, I allow 3 to enter. So 3 is more general. Because I can set my counter to 1, it becomes mutual exclusion, is that right? So let's talk about this different kind of semaphore. Now this semaphore, if the counter is bigger than 1, we call it counting semaphore. It has a different name, counting semaphore. Okay, so the counting semaphore, the counter starts with a number, let's say bigger than 1, let's say 3. Or I should put it bigger than 1. The counter cannot be 0, right? Oh yeah, the counter can be 0, sorry. But the counter cannot be negative number, it must be positive number. Okay? Any number that is bigger than 1, we call counting semaphore because it's actually a counter. Okay, if let's say the counter is exactly 1, right, we call binary semaphore. Okay, this binary semaphore, because the counter is 1, you can do mutual exclusion. Right? Because 1, you allow only 1 to enter. If 3, that means you allow 3 to enter, but this will not prevent mutual exclusion. Yeah? But semaphore is actually not, the idea is actually not to solve mutual exclusion, but it can solve mutual exclusion, right? Because it's more generic. Okay, so this is the, I should say here, initial enter. Because this value can change. Okay? Now let's talk about counting semaphore first because it's the most generic one. How does it work first, and then I'll explain why you need, and then I'll go to binary semaphore and show to you how this solves the mutual exclusion. And then later on, only I explain why do we need this counter to be bigger than 1. Okay? Okay? What does it solve? Because it's not solving mutual exclusion when it is bigger than 1. Okay. How does this counting semaphore work? We have a counter, and that counter has an initial value. Let's say the value is 3, right? Or maybe 4. So let's count here. So this is your semaphore. Sorry, semaphore. Your counter start with 3. Okay. Okay. When you create the semaphore, it basically is an object. It has an initial value as 3, and then whenever you want to use the resource, okay, you want to use the resource, you count the counter down by 1. So you do a down. There's a different term that is used here. Is wait signal or PV. Okay. So down can be also called wait. There's another term which we use in mutex later on. We acquire. Okay, these are the terms that we use. Huh? But down is easier to understand when we look at semaphore counter. Okay, but the different name. Huh? Down, wait. Here you use wait, and also we can call acquire. What does it do? First thing, it will check the counter. Is the counter bigger than 0? If it is bigger than 0, it will reduce by 1. So eventually, when you do a down, the counter will be 2. Okay? You will counter it 2 because it's not 0 initially, right? So you reduce by 1, and this thread can pass. It can go into the region. It's not critical region, you go into the region. You can actually access the code. Okay? So first thing you have to do is you have to look at the counter. If the counter is a positive number, it's not 0. You reduce by 1, and then you enter. Okay? So that is if it is the value is 3. But let's say, for example, after a certain period of time, after many threads already use up this, perform this down operation on this counter, and it comes a time where the counter is 0. Let's say the counter is 0 this time. The counter right now is 0. And when you perform a down, what is going to happen? Or wait, or acquire. Because it's 0, now it knows that there's not enough resources. So it has to wait. That's why here it's a wait, right? But we can use down, right? Down the counter, but if it is 0 already, it will not allow it to pass, and this thread is going to block. Okay? It's going to block, it will not run. Okay, the operating system will put it on hold. Here, when you do it down, because the counter was 3, it was positive, it can enter. It can enter into the region and use the resources. But if the counter is 0, then it block. Okay? So we can see from here, actually the counting semaphore is counting the number of resources. When you start with 3, it means that you got 3 resources. Okay? Now when you perform a down, okay, if it is not 0, then you can perform a down and you reduce by 1, and you can use the resource. And then if you count down to 0 and you perform it down again, you will not be able to acquire, you have to block. And basically that is the reason why another name for it is called wait. Okay? You wait if let's say the counter is 0. Why do you wait? Because you don't have enough resources. And will you be able to wake up or unblock? Yes, you can. How? Remember the 3, let's say it starts with 3 thread comes in, you'll take the 3 resources. So the 4th one comes in, will block. Right? So let's say this is the place where you do the down. Wait, acquire, right? So you got 4 thread that's coming in. But your counter initially here was 3. Okay? So 1 pass, here will be 2. Right? Okay. The next thread comes in, you look at the count, you do perform a down, and then it becomes 1. And that thread will pass. And you've got 2 threads that is passing, and then use the resource. And the third thread that comes in, you see a 1, you reduce it to 0, it itself will pass. Okay, so 3 thread is using the resources right now. So right now you've got 1 left. Okay? And this guy, when he sees 0, you block. You block here. Okay? So this counter 3 initially is meant to protect these resources here. This code here is going to access the resources, and because you've got 3 resources, only 3 threads can use it. Okay? Now how about this thread? This thread is waiting, right? When will it able to enter to use the resources? We have some code here. This code here is going to do up. Okay, or in this case here is signal. Okay, another term here is acquire, right? Okay, release. Acquire means get or take. Release means you give away. Okay. Okay, it is the same thing here. Why we call it down? Because the number reduced, right? Why you call it up? Because it increased the number. Okay, there is one term that is used. Another term here that we use is wait or signal. Why? Because if it is zero, you have to wait. If you don't zero, of course you can pass. Signal meaning that if you already finish using it, you signal the other to enter. That's why wait and signal. Okay? How about acquire and release? This is just terminology. Yeah? They all mean the same. Acquire because when you before you enter, you want to acquire the resource, right? So you request the semaphore to give you one. Okay? And when you release, that means you give away, you're done with the resource already. So you return, that's why it's released. Okay? So you can view it this way. This is just a terminology. And of course in an exam, I might be using this name, you should know that this means the same. Okay? Okay, when you perform an up, what happens to the counter? The counter will increase. Let's say this guy finished using the resources and now it's done already. Now you have to release by doing an up with the semaphore. So the counter right now will go up back to 1. Okay? So when it gets up from here, it's going to increase the counter back to 1. Now because this counter is 1, so this is the same counter. This counter is the same. This guy will just now you get blocked, right? Because it was 0. But anyway, this guy release, this thread release, and it become 1, and is able to use it. So it will continue to complete the operation to do the down. You go back to 0. Now it can pass. Okay? So you will enter. Right? Now this guy, let's say this guy finish. You do an up. You go back to 2, and you get out. Okay? And let's say this guy done. You go out as well. And this one will increase to 3. Sorry, just now it was 1, 2. I think I lost my count. Maybe it was 1, this one was 2. Sorry, just now it was 1, and this guy go to 0, right? It should go to 0. So the first one comes out will be 1, the second comes out will be 2, and the last one comes out will be 3. Okay, so they are making mistakes. Because when it enter here, I forgot to change this to 0. So eventually, when everybody release the resources, the counter is back to 3. Alright? So the number that you see here actually tells you how many left the resources inside here. Okay? And the maximum number of threads that can enter at the same time is 3 already because the counter is 3. You understand? Okay, so that is what semaphore provide. Okay, it's a generic way to implement mutual exclusion. Because if this counter is 1, then you allow only 1. Because you got only 1 resources that you want to attack. Basically this critical region. Okay? So this is more generic. This one is called counting semaphore. If the counter is 1, initial counter is 1, it's called binary semaphore because binary, either 0 or 1. Right? Only 1 will enter. So this will solve mutual exclusion. This one. Not this one. This one will not solve mutual exclusion. It's a generic one. This one is the one that will solve the mutual exclusion. Okay? And this mutual exclusion is the one that we apply to this critical region in order to allow only one thread to access, as we can see from this example. If we allow one thread to access, we don't have race condition. Right? Okay, so we binary semaphore, when you create it, you have to initialize the counter. If you initialize the 1, it becomes binary semaphore. If you initialize to any value bigger than 1, then it becomes counting semaphore. Of course, you cannot use this as mutual exclusion, only this. Okay. How about mutex? The number of what? Yes. We use this binary semaphore to control or to synchronize how many can enter into this region. This region of code. This region of code basically is using the resources. If let's say we got 3 printers, let's say here, the code is to print on 3 printers. Okay, you can have only one processor print on one printer, right? You do not want to have 4 threads come in, print on the 3 printer. Because the last thread is going to simply override. Let's say you choose the first printer, then this printer is going to print garbage because 2 threads is going to print now, right? So you just imagine that this code here is like using the resources like printer or file. Let's say you've got 3 files. You open the file, 1 thread open 1 file, okay, and then write the data inside. Okay, you can imagine it, right? So here you use counting semaphore is to actually share the resources. And you use binary semaphore actually also to share the resources as well, but more importantly is for mutual exclusion, to protect this critical region for avoiding race condition. Okay? Take note, counting semaphore will not avoid race condition because why? Allow 3 threads to enter, for example, in this case here. Right? And definitely you have race condition if let's say you share the data at the same time. But it's very funny, just now I said I got 3 printers around, right? And then I said you can share this 3 printer, how can you cannot? Actually, what you do is this. First you allow 3 to enter, yeah? And then you need to have a binary semaphore implemented inside here. You need still mutual exclusion, Why? Because you got 3 printers, now 3 threads want to use. But each thread do not know which one to choose. If let's say 2 threads choose one, you still have race condition. So you must make sure that 1 thread choose this, the other thread choose this, the third thread choose this. So you will have a binary semaphore in between inside here. Okay? So only 1 thread comes in, you choose the printer. Okay, once you select the printer is used already, then the rest of the thread that comes in will choose the other 2. So there's some kind of binary semaphore in between, inside here still. Okay? Here is to control how many that can enter at the same time. But inside here, there's a binary semaphore to control this critical region, which printer to choose for which thread. Okay? What? You want to make this code unparalleled. You want to make this code unparalleled. Okay, that's a good question. He asked me, since if you run this using 3 threads, you will encounter this condition, right? Then why not just use 1? Fair enough. Now, the issue is this. When you run the code, right? Say you run a certain code. You remember what we did? We compute the area of the triangle, let's say, for example, right? Now we can assign these multiple threads to compute their own separate rectangular, right? Because it can solve the problem faster. Is it correct? So this one needs to pairize. Do you agree? But inside the same code, we need to update the sum, the total sum. But let the total sum, all of them need to access at the same time. I mean, they have to act, but they cannot act at the same time. You need to make that critical region. You understand now? You cannot avoid it because the thread needs to update. But they cannot update at the same time. They have to update one by one. Because if they update at the same time, they have race condition. So you cannot avoid it. That means this critical region is meant for that. No. Not necessarily OMP parallel. This is more generic than that. OMP is basically a platform. Okay, it faces this problem. That's why we have to use this system, critical region, and this minus semaphore to help solve the problem. Okay. So his question is this: if we know already we cannot run the multiple threads here, why we want to allow it to run multiple threads? It's because we cannot avoid it. We want to parallelize this solution, right? So you have to run multiple threads. But running the multiple threads, while of course, when you calculate the rectangle, they can run at the same time. But then when you sum them, you are using the same variable, and that variable is something like this, right? So if everybody tries to sum at the same time, they will override one another. You get this kind of problem. So you cannot avoid. You have to use critical region. Sorry, you have to use binary semaphore to protect this critical region. Okay. So how do you use binary semaphore to protect it? You do a down here. So initially you initialize the counter to 1, so it becomes binary semaphore. Then you do a down first. So every thread that comes in have to do a down first. Okay. If it's successful, then you will enter. If it is not successful, you will block. Okay, the one that's successful is only one that can enter at the time. And you will perform this until completion, then you will do an up. Up basically is signal. It's signal to the others to enter. Okay, so let's say 3 threads come in, try to enter, right? But then there's some binary semaphore. You do a down, and that down will allow one thread to enter. The rest of the thread will have to wait, because now the counter becomes 0, one thread enter, right? So the rest have to wait. Now that thread that finished, you will do an up. That up will increase the counter to 1. And now the next thread can enter. The other thread have to wait still, because the counter now becomes 0 already. Okay? Once you get out, you do it up. Now the counter will become 1, and the other thread can enter this time. So by doing that, now your critical region is performing like this in sequential. Okay, so sequential like this, no race condition. So that's how binary semaphore able to protect this critical region. Okay, you do a down here, down on the binary semaphore. Okay, basically it's just I should write like this. Let's call it bin sema, binary sema, and you do a down. Okay, and then here bin sema. You do a up. Yeah? So when you create binary semaphore, maybe you create something. Binary semaphore. Okay, you call it bin sema, because that's the name of the object. And then when you start the value, you start with 1. It means the initial value is 1. You create binary semaphore, the initial value is 1. So you do a down. If it's successful, you enter, and then you do an up, so that the rest of the thread that comes in will be able to enter. Okay, but you will ensure only one thread enter. Okay, once the thread exits, you will signal to the others. Okay, so that is how the synchronization happens. Is that clear? Okay, right? Now here actually shows to you how actually it's implemented. Okay. While it is less than 0, you wait. See here, you wait. You wait here. Okay, you wait while it is less or equals to 0. Right? If it is not equal or less than 0, that means it's positive. Okay, positive number. Then you reduce by 1. Because when you enter the time, you have to reduce by 1. Right? So S minus 1. S is the counter. Okay? So basically, if let's say it's positive number, you reduce by 1 and you get out from this wait. That means you don't have to wait. Right? You just get out from there. Of course, here it's called wait. I call it binary semaphore. Okay? This one is signal S. Just a different terminology here. Okay? Now the signal The signal is very simple. You just increment the S, right? You just increment the counter. That's all that you need to do. So the rest of the track is going to wait. Now this one is called spin lock. The while loop there, you spin. Okay, you wait there. Actually, it's not efficient because the processor is wasting time there. Okay. Now this one is spinning, waiting. This one is not. This is blocking. Okay, blocking is better, more efficient than spinning like this. Blocking means you are telling the operating system. You actually allow the operating system to assign the CPU for other threads to run. The CPU can be used by multiple threads, right? If this guy is blocked, then the CPU is free, isn't it? Then you can assign the CPU to other threads to run. So blocking is more efficient than spinning. If you spin like this, the CPU is busy spinning, is wasting time there. Okay? So this implementation is not so good. The better implementation is blocking. Okay? Now blocking is the way that is all semaphores. Okay? This is just a simple example because it's easier to write. Because blocking, you have to use operating system function calls in order to block. And it's more difficult to show. Okay, so that is a semaphore, and this is how you use it. You create the semaphore, then you wait, you binary semaphore down, and you enter into critical region, okay, and then you signal, or you do binary semaphore up. Okay, so that is how you use it. Okay, this is one example, how you use, let's say for example, you got two ATM machine, okay, this ATM machine, let's say ATM machine, and this ATM machine, let's say, and of course they communicate with one another. There are two tracks running. So two tracks are running in this ATM machine, two processors, they are running at the same time. So they can enter into this balance equal balance minus the money that you withdraw. Okay? Let's say this guy withdraw 200 ringgit. This guy withdraw 100 ringgit. Okay? You take out the money. Right? So initially you got certain balance. Now two processors run on two processors, but of course two different ATM, of course they run on different processor. So they have to synchronize it. When they enter into this critical region, this critical region code, they have to make sure that only one track enter. Because if two track enter, you might lose money or you might gain money. Alright. Not because everybody is competing to subtract the balance. And this one is the same thing as what we see here. Right? Here you see only one statement, but actually in assembly, there are three instructions, and you have race condition. Okay? So in order to avoid race condition, you have to wait first, then you subtract the balance, 200, then when you signal, then the other process can enter. Now the other process enter, then when you subtract the balance, you get the correct balance. Okay? Right? Now, one question here, maybe maybe you missed it. I told you the critical region is a piece of code. So it looks like it's only the same code, right? But if you look at here, these two ATM is running on two different CPUs. Right? That means there's a critical region here, which is that, and another critical region there. These two critical regions looks like they are separate, two separate critical regions. No, they are actually one, right? The code is the same. Just that is two copies of it, right? Okay, so the critical region doesn't mean that one piece of code, no. It's actually a code that can be duplicated. You can duplicate that into different memory, right? And they are still one critical region. Is that clear? Yeah? Okay, so critical region doesn't mean that the piece of code must be the same code residing in one part of memory. No. It can be on different computer, it can be on different system, but they are still the same code, right? So they are still critical region. Okay? Okay, here the term is used is wait signal, and of course we can use another term, down, up, or acquire, release. Okay, how do we use this semaphore? When we identify the critical region, we know that this is the critical region, we have to protect it, right? And we know also, this critical region only allow one track to enter, is it right? Now the question is, like what you mentioned just now, right? We defeat the purpose now. We run the program, we want multiple tracks to run, or multiple cores to run, isn't it? But right now, when you enter into critical region, you have to go one by one. That means there's no parallel computing happening here. Is it correct? That means if your critical region is very lengthy, there's a for loop inside there, that means it's not good. Is that true? Because only one track can enter. There's no parallel computing that can happen inside there. Okay? So in the critical region, the rule is this. Although it's not written in paper or whatever, we know that we cannot have very complex code inside here. It should be short, it should be fast. Okay? Let's say, for example, when you increment A, isn't that short and fast? Yeah? Then we protect it using critical region. That is, okay? What we don't want is that there's a for loop inside this critical region. Okay, you have for loop and then everybody has to wait. It's not good, right? Another things that you don't want to put is this. If the code do not need to be protected, okay, do not need to protect it, don't put it into critical region. Because you put it into critical region right now, your critical region becomes bigger and bigger. You need more time to actually execute it. Okay, you only put things that is shared and you need to avoid race condition. Then only you put inside. Then only you can make this critical region small. Is it correct? So this is what it says there. Okay, make sure that it's short as possible. Okay, the implementation is short, and you don't want to use critical region as much as possible. If you do not need to use, don't use. Because once you have critical region, it means that there's slow down. It will slow down the system. Okay, this one has something to do with producer consumer. I'll explain to you later when I talk about it. Yeah, I'll skip this. Okay, let's go back to this term here. Okay, I mentioned to you just now using counting semaphore. Counting semaphore, just to recap again, this counting semaphore is counter greater than 1. It would not help mutual exclusion. If you want mutual exclusion, you have to use binary semaphore. Is that correct? And the counting semaphore is actually to control the number of threads entering into the region. Okay? And the number of threads, you can choose how many. You can choose 3. If this is 3, then you will be 3 inside. If you choose 2, you will be 2 inside. If you choose 1, there's 1 inside. And 1 is a binary semaphore. This is a special case. And binary semaphore can be used for mutual exclusion to avoid race condition. Is that clear? Okay. Before we get into here, there's another thing that I want to talk about, some binary semaphore. Binary semaphore. Let's go up here. In certain kind of synchronization, you want something like this. Let's say you have something here, right? You need to process this one first. You need this process A to process this first, and then you pass this process data to another process. That's called process B. Then you process it, okay, and then this will be the output. Okay? So process A will take the raw data from somewhere, you process it first. Once it's done, you pass that data to another process to continue. And then of course, it is free right now, you can take the next data in. Just like in the factory, right? One person feed the tire, the other person feed the body. Once it's finished, he passes to the next guy to actually fit the body, right? Or he fit the tire for the next car. So it can be something like that. So it is still run in parallel, right? But each process is doing different things. Now this process here has to wait for process A to complete first. It cannot do this data immediately. It has to wait for process A to finish first. So somehow this process needs to signal when process B can start, right? When does it? When process B can start? After I process A finish. When it finish, it will signal to B. Right? Now you can see just now you have this signal there. Now you can use semaphore to actually solve this problem. Okay, this is another synchronization problem. Okay, just now the synchronization problem is to solve this condition using binary semaphore. We can use semaphore to do another kind of synchronization, which is signal. Okay, I finish. I signal to you. Now I give you this data. I signal to you, and then you start. But you have to wait for my signal. If I don't signal you, you have to wait. Okay. So how does it work? Process B will do the something is wait. You wait for the semaphore. Let's use this term. You wait for the semaphore, and now only you do the process. Okay? Process data. Let's say the data is D. So you have to wait first. If the signal doesn't come, you wait. If the signal comes, you process. Alright? And of course the data will be passed here so that you can do it. How about this guy here? This guy will process first. Okay? Process data first. Of course, he processes with own algorithm. This is a different algorithm. This is a different. Okay, and here you signal. Signal as. So you process the raw data. Once you finish, you signal, and this guy will start to do. And why do we have to do this? Because when you run in parallel, they all run at the same time. Right? If this guy is faster, if you don't have wait there, you process the data, but this data is not there. Right? Because this guy runs faster, because they run in parallel. That's why you need to synchronize them. Synchronization here is this way. So it comes, no matter how fast it comes, you have to wait. Because nobody signal, he has to wait. So this guy will process first, and then he signal, and this signal appear, and then it will start to run, and it will run this process. So you can see that this will happen first, then only this, always. No matter who run faster. Is that correct? Yeah? Now, how is it different from just now? It's different is because when I create this semaphore, I use binary semaphore, but I start with 0. Okay? That one, I start the binary semaphore with 1. But when I start with this binary semaphore, let's call it semaphore, I put 0. Okay? So S is a binary semaphore, this is semaphore, and the counter is 0. Okay? So when I start with 0, why do you need to be 0? Because if let's say this process B is faster, S is 0, so you have to wait, because it's 0. Is it right? You know? So it must be 0, it cannot be 1. Right? If it is 1, then it will enter into this code here and process the 1, which is not right. That's why you have to start with 0. Okay? That one is different. In binary semaphore here, the initial counter needs to be 1. Right? Because if it is 0, if it starts with 0, everybody comes in, everybody waits. Nobody can pass. It's wrong. Right? Here is different. Here you cannot start with 1. If you start with 1, this guy will not wait and you will enter. You have to start with 0 so that you wait. Okay? And then this guy process, and then you signal by increasing to 1. And this guy, because it's 1, right? S is 1, so he will get released and then you process. Of course, when you process, this will go down to 0. Yeah, for this signaling, yes. It is for semaphore. Correct. because you want process B to block first. If he's faster, he will block first. Right? You cannot start with 1 here. Okay, if you start with 1, this signaling will not work. That one, critical region, you need to start with 1. If you start with 0, everybody block and nobody enter. Okay, so everybody block is called deadlock. Okay, there's a term that we're going to touch later on. It's called deadlock, and it's a problem. Okay, so now I'm finished with the semaphore, counting semaphore and binary semaphore. Is that clear, everybody? Make sure you're clear, because this one sure will come on an exam. Okay, I mean the concept, you need to understand the concept. Okay, once you understand the concept, we should be able to answer the question. Okay. The next thing I want to talk about is mutex. Take note that this mutex is actually an object similar like semaphore. We can think about mutex as mutual exclusion, but actually this two is different. It's different. This is a terminology. Mutual exclusion means you allow one to enter, you block everybody else. That is mutual exclusion. That means it's mutual. Every thread must have mutual agreement among themselves. If one enters, the others is excluded. They cannot enter. That is mutual exclusion. Okay, but there is one object to actually protect critical region, and it happens to call mutex as well. And this mutex should be derived from this name. So please make sure that this is the concept that I was talking about. This mutex is an object, okay, to implement mutual exclusion. Okay, mutual exclusion. Okay, this object is the same as this object. Why do I say it's object? Because when you create binary semaphore, isn't it this object? This object, isn't it? This object that you use to perform the down. It's the same thing as the mutex. We have mutex, which is an object, to implement the mutual exclusion. This is the concept. Okay, it just happened that the name itself is kind of misleading. Because when you say mutex, you assume that, oh, that's mutual exclusion. This is the object to implement this mutual exclusion. Okay? Right. Why do we need this mutex here? The reason is this. Programmers always make mistakes. Even seasoned programmers also make mistakes. I also make a lot of mistakes, right? Okay? And if you look at the binary semaphore, counter semaphore, you can easily make mistakes. Why? The reason is because binary semaphore, you can set the counter any value that you want. You can set to 1, you can set to 0, you can set to any number, right? And another thing is, if you look at this one, okay, you perform the signal first, then only perform the weight. If you look at the critical region, you have to perform the weight first, then only signal. It's the reverse of that. That one's weight first, then only, weight and signal is done by two separate processes. Okay? Process A do the signal, process B do the weight. But here, the thread that do the weight is the same thread that do the signal. The same thread that do the weight or down is the same thread that do the up or signal. Is it right? But that one is different. Two different processes. One is doing weight, the other one is doing the signal. Right? Okay, so you can abuse this and you can get into trouble. Okay, because you can do something like this. Let's say, for example, I have binary semaphore, which is 1. Yes. I do a down, and then I do a down again. What's going to happen if I do a down the second time? First time when I do a down, because binary semaphore is 1, it becomes 0. And I do a down again. It's kind of stupid to do this. I do a down again, it becomes 0. What's going to happen? that thread is going to block. Is it correct? First, I do a down from 1 to 0. Okay, I can pass. First it was 1 before, huh? But now it becomes 0, and I do a down again. It's already a 0, so I will block. So once it blocks, it will never get into critical region. Whoever comes in will block also. Right? Of course, this is silly, and this is a mistake. It's potential mistake. Okay? Another thing is this. You can do a down. Before you do a down, you can do an up first. Okay? Let's say what if you do like this. If let's say you make a mistake. So you go up here. From 1 to become 2. Right? So it becomes 2, so because it's 2, so it's going to enter, right? Right? So now 2, because 2, the other that comes in will do up, become 3, and you will enter as well. So right now it's not protecting the critical region because of this mistake. Is it correct? Okay, so the programmer, the developer who developed this, they know that you're going to make this silly mistake. So how to avoid it? To avoid it, we have to constrain. We must make sure that we don't do these silly things, and we don't do double down. Okay? Of course, programmer, you cannot tell the programmer, hey, don't do this. You don't tell that, the fellow will do it. Somehow the fellow will do it. Right? For example, I tell you, don't do this. Later on, I see somebody else do it. Okay, so I cannot avoid you from doing it. I know that you're going to do this silly mistake. So how, as a developer, how do I create something that is more safe to use? That is when the mutex comes in. So mutex is actually something similar like binary semaphore, but it's safer to use. So we cannot make this kind of mistake. So let's see. First thing is this. We create the mutex first. It looks like this. We call mutex. Let's call it mute. And we don't have to give number there because the counter is always 1. It's always initialized to 1. So you cannot make this silly mistake by putting silly number inside. You cannot put 0, you cannot put 1, here you can make a mistake, right? Here you cannot make a mistake because there's no way for you to initialize the counter. The counter is always initialized to 1, and therefore it will always be binary semaphore. Okay? And then, let's say this is the critical region. Okay. And I do, okay, in mutex we don't call down, up and all that. We call acquire. We use this, the third term, acquire. Okay, and another name for acquire is lock. Okay, lock. So you see this term, either acquire or lock. Okay? So when you lock, meaning that you try to lock and you enter. If let's say it's not locked, you can enter, then you block the rest because it's locked when you enter. When you get out from this critical region, you do a mutex release. Okay, another term for release is unlock. Okay, you see these two terms that is used. Okay? So this is the proper way of using it. Okay. Just now I told you the silly way, right? I do a down here and then I do a down again. And the second down will cause it to block. And it's dangerous to do this, right? But what happens if I do the same here? I do mutex acquire again. Will it block? Will it block? No. Because mutex know that you already locked just now, you will not lock again. Okay? So that is what mutex provides. Okay, and how does it do it? Because when you do the acquire, right, it will record one thing. Whoever you ask, you check, who is this track that is locking? Okay, when you acquire, you check who is the one that you asked to to lock. Okay? And then we acquire the second time, you check. Oh, it's the same guy who actually locked, so it will not lock. You understand? So that's how it actually represents. So somehow, when you acquire, when you do mutex acquire, basically the thread has the ownership, owning this. So the thread is going to own this ownership on this mutex. Binary semaphore, no. Binary semaphore has no ownership. Okay? The thread does not own this. So any other thread can do a down or up, or it itself can do another down. This guy, this mutex is different. It's owned by this mutex. When it do another down, this mutex will check, are you the owner? You say, yeah, you're the owner. So you will not do the second down. You just let it pass. Is that clear? Okay, the same thing here. Mutex release, you can release the second time. But it will not increase this twice. Like for example, you do up here, it become 2, isn't it? Here no. You check first, are you the owner? If you are the owner, you can only release one time. Once you release, you're no more an owner. You're no more an owner of this mutex. When you release the second time, you say you are not the owner, so you cannot release. Okay? So you can do this silly mistake, but it will not cause any problem. But if you use binary semaphore, you do this silly mistake, you will get into trouble. Either the program doesn't work, or you have you're not protecting this critical region. In this case, you have this critical region is still protected, even though you do this silly mistake. Okay, because of the ownership. So once the thread own this mutex, okay, the mutex can check. Okay, when you acquire the second time, and you will not block it. The same thing here. When you release, you're not the owner anymore. You cannot release the second time because you're not the owner. Okay. Now, then let's have a look whether this mutex. Remember, I mentioned about this signaling here. I use semaphore. Initial value is 0. And I'm playing with 0 and 1 as well. Right? It looks like binary semaphore, but actually it's not. We start with 0. Can I use this mutex to solve this problem? Can I use it? Like for example, I do like this. I use signal, right? But I don't want to use signal. I use mutex release. Okay? And then this, instead of that, I use mutex acquire. Okay? Assuming that the mutex is 0, when I enter, I cannot acquire because it's 0, so you block it. Right? And then this guy will release. So that this guy can move. Right? Okay, it looks like it is possible, but actually cannot. Right? 2 reasons. The first thing is, remember I told you that this mutex, you cannot change any value. Always start with 1. This one you need to start with 0. So it cannot be used. Or even though it can be used, let's say for example you can set it to 0, right? So also cannot be used. Why? Because in order to release, you need to own this mutex. In order to own the mutex, you have to acquire first. Okay? That means you cannot do something like this. You cannot do mutex release and then mutex acquire. You cannot do this. Right? Because the order is different. Right? You cannot release before you acquire. You have to acquire first in order to own this mutex, then only you can release. So if you are not the owner of this mutex, you cannot release. You will not release. When you acquire, then only you become the owner. Then you go, the counter will go down by 1. Okay? So it means that mutex can only do mutual exclusion. It cannot do signaling. Whereas binary semaphore, you can do all. So binary semaphore is more robust. That means you can use it for any kind of synchronization that you can think of. But mutex is only meant for mutual exclusion. You cannot use it for any other thing. It's meant to actually also protect you from doing this kind of silly mistake. Okay? Right? Is that clear? Okay. Let's move on to the next topic. I have 15 minutes. I know I talk very long here because I need to make sure that you understand. Yeah. How do you create new text? How do you make this kind of mistake? If let's say your code is very lengthy and you have followed here your if statement, for example, right? Then you might miss it. Let's say, for example, if condition is true, only apply. Otherwise, you don't apply. Right? And if your program is very convoluted, it's very hard for you to know whether you acquire or release. Because you've got if-else statement, for loop, while loop everywhere. So you can make this kind of mistake. Okay? Now, of course, mutex, it can prevent certain problems, but it cannot prevent other problems. For example, like this. If I do this, you've got problem. If this is critical region, right? Instead of doing acquire, enter into critical region and release. That's the proper way of doing things, right? But you release first, enter into critical region, acquire. Now if you do this, then this critical region is not critical region anymore. Because many threads can enter. Right? First thing is, mutex release, you're not the owner, so you cannot release, so you pass. So every thread that do this will pass and it will enter into critical region. So you have race condition there. And everybody acquire. But the first one will acquire successfully and pass, the rest will block. But this guy here will not release. So the guy who get blocked here will encounter deadlock. Okay, you're locked forever. Okay, so this is another mistake. And we have another object which can prevent this. I will explain to you later, and we will use this often also in practical. That is a monitor. Okay, we will cover in the next chapter to overcome this problem. Okay, let's come back to here. I've got 15 minutes. Hopefully, I can finish this on time. Lock. So, what is lock? Just now I talked about this mutex binary semaphore. Actually, is mainly implemented using a single core. You got multiple processors, but it runs in a single core. Okay. You can implement it also for multi-core as well, but mainly is meant for a single core. Okay, but for multi-core, most probably you would not want to use this binary semaphore, even though it supports multi-core, because of efficiency. So let's see another way to do major exclusion. We're going to use lock. Maybe I back off here. So how does lock works? Very simple. You just have let's call it lock. We put it as 1. Okay. And here you check while lock is less than 0. Okay, sorry. Is just like what you saw just now. If lock is 1, okay, sorry, not equals to 1, then while lock is 0, okay. Right? So this piece of code is atomic step. Okay, why it is atomic step, I'll explain in short, but let's see how it works first. It works like this. If the lock is not 1, that means somebody has locked it. It will be 0. And here, actually, you check. If this lock is still 0, you loop, you wait. So this is called spring lock. Right? So the correct term here actually is spin lock. It's not lock. It should be spin lock. Okay? So spin lock works like this. Initially is 1. It's just like what we studied just now. Just like binary semaphore. And it will spin when it is locked. This one will not spin. This one it will block. So it's different. This one spin lock when it is waiting. This binary semaphore or counter semaphore, when it is waiting, it does not block. Sorry, it does not spin lock, but it block. Block is more efficient. Why? Because when you block, the CPU is free, right? The CPU can run other threads. Spin lock is different. The CPU is busy checking this lock. That means the thread is actually still running. It's not blocked, but it's keep on checking. But it cannot go far. It can stay here only. Because every time you check, it's 0, right? So it won't block. Once it becomes 1, then only you can enter. Then one, of course, when you enter, you will assign. Sorry, I made a mistake there. There's another step here. After this while loop, there is lock equals to 0. Here you have to assign this to 0. So it is the same concept like binary semaphore. The only difference is this one, the block is more efficient because the CPU is not wasted. It will be used by other thread going to run. Here is different. Here the CPU is wasting time checking this lock. Okay, if this lock is 0, it will spin. That's why it's called spin lock. Okay. Now, why this one is useful? The reason is because you got 2 processors. Let's say here is processor 1, or I call it a core 1. Okay? 2 different cores. 2 different cores. And here there's another core. This core also will have this similar code here. Okay? And when it comes, of course, it's the same lock. That means this lock is shared between these 2. You will check if this guy is managed to get through, it will lock, isn't it? Because lock is not equal to 0. Sorry, I should look at this better. 0. Clearer. If it is 0, you will wait. If it is not 0, you will enter and then you lock it by assigning to 0, because initially it's 1, right? So assuming that the same code here, but 2 different cores. This core number 1, this core number 2. If this guy comes in, because it's 1, you will lock it, so it will enter the critical region. When this guy comes in, of course it's 0 right now, you will spin lock here, right? So these 2 cores is 2 different cores. When you finish, this guy will release it. You set lock to 1, and right now it's C01. You will get out from this while loop, and then you lock, and you enter into critical region. So it's the same thing as the binary semaphore, except that this is a spin lock. Okay? Why is it useful? Because this blocking is efficient, but it's slow. Because you have to call the operating system. The operating system has to save your contacts, save it to the memory, and then load the other processor, other chunks into the CPU, and then run. So blocking is not efficient. Spin lock is efficient, especially when your critical region is very, very short. Let's say only 1 or 2 cycles. Okay? If it is 1 or 2 cycles, you prefer to do spin lock rather than binary semaphore lock. Because blocking, in order to block the thread, it takes a lot of cycles, maybe 1,000 cycles, just to block the processor. Here, if the critical region is only 1 or 2 cycles, then it's better for you to spin here temporarily. Okay, because you know that you're going to spin only 1 or 2 cycles before you enter. This is more efficient, right? Okay, and you can see using 2 cores, you don't have very complex kind of synchronization like blocking. Okay, because this is just spinning only one instruction. So first thing is simple to implement. is very fast and very useful, especially if you're multi-cores like this, and your code here is only very short, 1 or 2 cycles. Okay, majority of your critical region is something like this, which only take 2 or 3 cycles to implement. So spin lock is useful. The critical region is after this. Okay, and here is going to be how you release the lock. When you release the lock, you set the lock back to 1. Okay, so this is acquiring, enter into critical region, lock. The same thing, this core also doing the same code here, critical region, then unlock. So this is unlocking, this is locking. Okay, so only difference is this part here. Actually, it's more or less the same. I mean, the effect is the same, but the way you implement is different. This one is expensive to implement. Okay, it's useful if, let's say, your critical region is quite kind of lengthy. Okay, let's say you've got a little bit more code, then it's useful to use block. Okay, because if, let's say, because when you block, if, let's say, you take quite an amount of time to enter into critical region, that CPU can be actually used for other purposes, right? Because if you spin lock here, that CPU is wasted. Okay, so you want this critical region to be very, very small. Let's say 1 or 2 cycles, or 3 cycles, or maybe 10 cycles. This one maybe 100 cycles, or 200 cycles. Okay? As I said before, of course, we want this critical region to be as small as possible. No? But if you look at our code, this critical region is not small. It can be quite big as well. Okay? Even though we strive to make it small, but sometimes you cannot have a very, very small. Okay? So spin lock is useful for multi-cores especially, and then here is a small number of code in the critical region. Okay? The concept is the same. I won't explain. This one applies to lock, spin lock, applies to binary semaphores. Okay? Now, one thing that I mentioned just now is this here, atomic stack. This one is also atomic stack. You will see, I think it mentioned atomic stack somewhere. Is it? Why is that so? No, you don't mention. I think somewhere you mentioned atomic stack. Is there any atomic stack? No. Oh, that atomic lock. Okay, atomic lock. Okay. So why this atomic stack is important? Remember I mentioned to you, this code here actually is 3 separate assembly language, right? And if you run multi-cores, then they can run at the same time. Okay? This also, if you look at it, there are multiple statements here. Most probably it will be multiple assembly language as well. Is that right? But because this is atomic stack, meaning that the processor will ensure that this is one in one step. Okay, you run in one step, and that means there is a special instruction, special assembly language for this. Yes, only one instruction. Here there are 3, right? Even though I write down here 3 or 4 steps there, but there is an efficient assembly language in all the processor, including x86 and x64. It's only one instruction, so that it can run in atomic step, one step. That means there is no way for the processor to run at the same time. Okay, they have to run at different times because it's atomic step, right? So this is useful because it's supported by the processor. The processor has these little facilities implemented inside the assembly language itself. Okay, you don't learn this in your assembly language subject, but if you go and check, you can find. Okay, so this atomic step is important because if you cannot execute in atomic step, then while you are checking and you are changing, somebody else will go and override it, and then you get different results. And you have race condition inside this block itself. Okay, So this atomic start is important because you do not want race condition to happen inside the spin lock. Okay, because you are supposed to prevent race condition, right? So you cannot have race condition happens inside your spin lock itself. So that's the reason why you need this to be in atomic start. You have to execute in one step. Okay, I don't have enough time. I'll continue next week. Okay. Yeah.